Alright guys, in this video we're going to be looking at some forces problems. We're going to have to solve them
by our knowledge of the Force.
How do you know this?
He knows the ways of the Force.
That's good news.
So get ready to give it a try.
Alright, I'll give it a try.
No! Try not! Do! Or do not. There is no try.
I work with a bunch of nerds.
Roll the intro.
Do you feel the vibes?
Now, you might have understood kinematics pretty well, and start to think.
You know, I'm something of a scientist myself.
And you might even see the first part of forces and think the same thing.
Bad news, everyone!
These can get pretty tricky. That's because force is a vector, and so we have to treat it in multiple different dimensions as long as it exists in multiple different dimensions. But I'm getting a little bit ahead of myself. Let's first start with the basics. There are 4 steps to setting up forces problems before you can really solve them. The first one is to simply identify all the forces that are on the object. So look around. Make sure that you catch everything that's touching the object. The floor, anything on its sides, anything above it, if a person's pushing on it. Also, never forget about gravity. Gravity is important. Step 2 is to draw a free body, or forces, diagram. For a free body diagram, we look at the center of mass of the object, which for most of the objects we're going to look at in this class is just the geometric center. We make a dot. And on that dot, we put all the forces that are acting on the object. So let's not forget about gravity. And we just draw an arrow where that force lies. And then we label the force. This will help us out later, as it will help us see where all the different forces are. So let's say we have an object that's sitting on a table. You know, maybe it's a giant square object. Well, its center of mass would be here. And now we can draw all the forces acting on that object. So, of course, there's gravity, and then there will also be a normal force. Now, the size of the arrow should theoretically relate to the overall force on the object, but that's not always going to be the easiest thing to judge. So just do your best. It's okay if it's not perfect. You might think to yourself, I don't need to draw this stupid diagram. I know exactly what all the forces are. I can clearly see that there's a gravitational force and a normal force on this block. And yeah, sometimes you just know what they are. And sometimes it's really complicated. So just draw the stupid diagram. It's really not that hard. It takes like 4 seconds of your life at the most. Draw the stupid diagram because it's going to help us out in step 3. Step 3 is to apply the coordinates. We're going to be setting a coordinate system for our entire system. And then we're going to be breaking up each individual vector so that they lie on one of those coordinate axes. For our block problem, defining a coordinate axis is very simple. We simply pick this direction to be positive in, let's say, y. That means that this direction going down is negative in y. And our vectors already lie along that axis, so we don't really have to do anything extra. The part where it gets complicated, though, is let's say we have a different situation. In this different situation, we're going to have something sitting on an inclined plane. Now, an inclined plane is just basically a triangle wedge. So we'd have some angle here. Now, if I have my block sitting on my triangle wedge, and I look at all of my forces, I will notice that I have a force of gravity going down, and a normal force going up and to the left. That's because the normal force is always normal or perpendicular to the surface, and in this case, the perpendicular to the surface direction is up and to the left, and the force of gravity is down. You may note at this point that we don't have 2 vectors that are sitting on a coordinate plane, so we have to make our own. Now, one thing that I really like to do, because it will help us later on, is define the direction of the acceleration to be positive. Now, in this case, I have to figure out which way my object is going to accelerate. Now, if you have ever put an object on, an inclined plane like a hill, you know that it goes down the hill. So my acceleration should be this way, down and to the left, which means I want down and to the left to be some positive direction. This means that later on, when I look at Newton's second law, I'll have a very defined direction for my acceleration. So I'm going to make my coordinate axis on a slant like this.
Can you do that?
Yeah, you can certainly do that. All we are doing is taking our coordinate plane and putting it along the axis here of our system. So I'd have up being, say, this direction, and positive x being this direction. So negative x would be this direction, and negative y would be this direction. So this is positive y, positive x, and negative y. Now, you might be thinking that this is definitely wrong, because positive x should be to the right, and positive y is at a completely weird angle, and all this kind of stuff.
For certain are you? Always with you what cannot be done. Do you nothing that I say?
We are allowed to set our coordinate axes really wherever we want, as long as it's in 2 dimensions. As soon as we move to a 3-dimensional thing, we'll have to deal with permutations of correct axes and stuff like that. But with 2 axes, it doesn't actually matter, because we can always rotate where our 3rd direction is. So we can pick whatever we want. So in this case, where you are used to x being this way and y being here, all I have done in order to get from here, from this axis system to the other one, is I have rotated my y by the angle of this inclined plane. And then that will make the inclined plane line up with our coordinate axes. So this here would be my theta that I have moved. Then that makes everything that was at this weird angle of our inclined plane along my y direction, which will make my life so much easier later. Now, when it comes to the x direction, that means that the x direction has been rotated. But you'll notice that the x direction is negative of what it used to be. So here I'll have negative x, and here's positive x. But all I did was flip it around. So basically, I just rotated my axis in y, and then completely did a 180 directional flip in x, where I just rotated it around x. This doesn't actually give me a different coordinate system. It just rotates and changes the one that I already had to better match my system that I'm trying to analyze. So let's now complete this step 3. We're going to complete step 3 by looking at our force diagram. So the force diagram, remember, had the normal force pointing up and to the left, and the gravitational force pointing straight down. Now I'm going to apply my coordinate axes, which means that y will be along the direction of the normal force, and then negative down, and x will be positive to the down and to the right direction, and negative up and to the left. So that means that in the y direction, I just have Fn and a component of Fg, so I'm going to say Fgy. So that means that I need to break up Fg into Fgy and Fgx. And since I rotated my coordinate system by this angle of the incline, that means that if I look here, this is Fg on my original picture. My coordinate system is here. So this angle right here will be theta, which means that this angle of FG with the vertical is theta, not the horizontal angle. So this is going to mess with our SOHCAHTOA, because you are used to cosine being the x direction and sine being the y direction. But in this case, we're going to get FGY is equal to FG cosine theta, and FGX is equal to FG sine theta. This is because the angle is adjacent to the vertical, not adjacent to the horizontal. So remember that what governs it is not x direction is cosine and y direction is sine. It actually has to do with which angle you are given. So make sure that you get that correct. So now we have a different force diagram, which we can look at this way. I'm going to put it down in this bottom right-hand corner, where we have, well, not force diagram, but we have a different looking diagram altogether when we look at this on our coordinate axis. So we'll get Fn, we'll get FGX, and we get FGY. And then this gives me all the forces along their coordinate axis, which is basically what step 3 is: to find our coordinate system, apply it to our system that we have, and then break our vectors up into their x and y components so that we can analyze it in step 4. Step 4 is to use Newton's second law and then apply it to the directions that we have on our diagram. So in step 4, we're going to go back to formula.
Back to formula?
Yeah, so what we're going to do is we're going to take our picture that we've made now of our coordinate system that we've created and our forces applied to that coordinate system, and we're going to use Newton's second law to create equations in order to represent our system based on this coordinate system. So I'll start with my y direction. You can see that in the y direction, I just have two forces. I have the normal force going up, which is positive, and the gravitational force in the y direction specifically, which is negative. And this is equal to the sum of the forces in my y direction. And that should equal, according to Newton's second law, my mass times the acceleration in the y direction. Now, I know that the acceleration in the y direction, because it's not lifting off the inclined plane, and that's the direction I've defined as y, is 0. So my acceleration in the y direction should be 0, which just means that the force of gravity needs to be in the y direction, just needs to be equal to the normal force. So we can use this to figure out the normal force. If you remember, the normal force is variable, which means that it doesn't have an equation that we can typically use to find it. So in this case, the normal force is only equal to the gravitational force in the y direction. Now, that's not really what we cared about for this particular problem. We want to know basically what the acceleration is down the incline, because that's really what you're going to be trying to find most of the time when you're looking at these forces problems. So let's apply this to the x direction, because that's the direction we defined as our direction of our acceleration. So I know that max is equal to the sum of the forces in the x direction, which is equal to, well, I only have one because of the direction system that I made. So FGX. And this brings us to our final step, which is simply to plug in everything we have and solve. And this FGX is going to be FG times the sine of the angle of my incline, as we can see in the left over here. So that means that MA, because the x direction is the only direction that has an acceleration, so the total acceleration will be FG sine of theta. Now, I know that Fg is a non-variable force, meaning it always has a value that we can define based on some equation, and that equation is mg. So I'll get that ma is equal to mg sine of theta. I can cancel my m's, And I just get that A is equal to G sine of theta. And that's it. Those are the 5 steps that you need in order to solve forces problems. Now, in our next video, we're going to look at a couple examples, which will hopefully bring this a little bit more to light for you. We're also going to look at systems which involve more than one object. So far we've dealt with multiple forces. Now we're going to deal with multiple forces on multiple different objects that are all interconnected and part of a system. So that's our next video. So stay tuned and check it out. All right, don't forget to like, comment, and subscribe. I appreciate it.